In this video, we're going to be exploring what's called the integral test. And this looks really complicated, but it's actually very simple. So this first slide is sort of the formal presentation of the integral test. So suppose you have an infinite sequence a sub n, right? Now I want you to think about the function f of x, which is equal to a sub n for all x equals n. In other words, the function is the same thing as the sequence, like term for term, they're the same thing. So your sequence might be 1 over n, your function would be 1 over x. Your sequence might be, n plus 1 over n squared, this would be x plus 1 over x squared. They're just different representations of the same things. So if you've got a function like that, where your function is the same representation as your sequence, if that function is strictly decreasing, beyond some point, beyond 0, then your infinite series will converge if and only if your infinite integral converges. In other words, the infinite series and the improper integral will both converge or both diverge. So, to run this by you again, actually in the next video I'm going to be talking about, right in the next slide, we're going to talk about how we use this test. So let's look at that. So the way we use the integral test, if the sequence you're considering resembles an integrable function, right? So suppose you're looking at some sequence, somebody wants you to do, the sum on n equals 1 to infinity of 1 over n. You look at this and you're like, hey, wait a minute, 1 over n, that reminds me of 1 over x. And I know how to do the integral of 1 over x, right? If the sequence you're looking at resembles an integrable function, write your sequence as a function of x, and then take the improper integral. If that integral diverges, the series diverges. If the integral converges, the series converges. Right? Then that's it. That's the integral test. It's incredibly simple. As long as you have a function, as long as you have a sequence which resembles an integrable function, and it's a decreasing function, do that infinite integral with the same bounds from 1 to infinity, and these two things will do the same thing. They will either both converge or they will both diverge. You're done. Alright, so determine the convergence or divergence of this infinite series. We have the sum from I equals 5 to infinity of the natural log of I over I. Right? Hopefully we look at that and we're like, I could do the integral test. And that's actually something I recommend that you guys do. When you're going to do a test, sort of write down, remind yourself, hey everybody, I'm doing the integral test. Then do the integral test. We can look at the integral from 5 to infinity of the natural log of x over x dx. Okay? And you all, I hope, remember that when you have an improper integral like this, we actually need to rewrite it as, the integral from 5 to a with the limit as a approaches infinity. And then we'll need we'll have to figure out how to do the integral of the natural log of x over x. This is going to be a U-Substitution. We'll let our u be natural log x. du is 1 over x dx. So that means that x du is equal to dx. So when I bring this back to the problem, I'll have the integral. I'm going to leave the bounds off. So this will be the integral of u over x times, and then my dx turns into x du. And that's super convenient because it means that these x's are just going to drop out. What I end up being left with is, let's see, I'd have the antiderivative of u du, which ends up being 1/2 u squared. But remember, my u was natural log x. So I end up with 1/2 the natural log x squared. And this is evaluated from 5 to a. And we're supposed to be taking the limit as a approaches infinity. So for this section in here, I left off the bounds because I didn't want to convert them with a limit in there. I just put my x back in, and now I'm using my old bounds, and that limit is still there. So we carry on. We have the limit as a approaches infinity of 1/2 the natural log of a squared minus 1/2 the natural log of 5 squared. And at this point, we sort of have to process what happens. What happens is a approaches infinity. We have the natural log of infinity. Well, if you picture the natural log function, natural log goes like this. As we go towards infinity on the x-axis, the function is going up towards infinity. That means that this right here is infinite, and I have infinity minus 1/2 the natural log of 5 squared. This clearly diverges. I suppose I should say the integral diverges. And so because the integral diverges, what does that mean about the original series? Right? It means my original series diverges. This means that the sum on I equals 5 to infinity of the natural log of I over I diverges by the integral test. And remember, when you finish these problems, I sort of want this full statement of what the series was, what happens, and what test was used to show that. Okay. So I have one more example of the integral test, and it's actually a pretty simple one. So if you guys would pause the video and try this one out and see where it takes you. So for this one, we again know that we want to do the integral test. The reason that we know we want to do the integral test is that this sequence here looks like 1 over x squared, which is really easy to take the integral of. In fact, it's a lot easier than the last problem that we had. So I will do the integral from 2 to infinity. And actually, I'm not even going to put infinity up there. Let's put 2 to a with the limit as a approaches infinity of 1 over x squared dx. So I have the limit as a approaches infinity of negative 1 over x evaluated from 2 to a. So we still have our limit. The limit is a approaches infinity. What we have here is negative 1 over a plus 1 over 2. And now as a approaches infinity, this first term gets incredibly small. This ends up being 1/2. Now I got to be really careful here. The integral converged, and that means that the series converges, but the series does not converge to 1/2. So I just want to make sure I'm very, very clear about this. With a geometric series, we can tell what it's going to add up to because we have that formula, right? We had that formula S equals, U1 over 1 minus R. That only applies to geometric series. In a geometric series, we can find out what it adds up to. With the integral test, we can't. We just know that because the integral converged to 1/2, the series will also converge. But we do not know that the series converges to 1/2. The integral test doesn't tell us that. All it tells us is, hey, congratulations, the series converged. Okay? So long story short, integral test, if you look at your sequence or your series and it looks like you can take the integral of that, try it out. The integral test may be a good way to go.